Hello, everyone, and thank you for joining us today for our Quantum Speaker webinar series hosted by ATARC's Global Quantum Working Group. My name is Lily Chen. I'm the group's government co-chair. We are very excited to welcome Evandro Rosa to speak with us today. Evandro is the Chief Technology Officer at QuantLoop. In this talk, he will explore the quantum programming stack, focusing on the software infrastructure needed to develop applications accelerated by quantum computers. He will break down its key components and explain how each one plays a crucial role in making quantum computing practical. If you have a question, please feel free to use the Q&A feature. We will save the Q&A for the end. Now the floor is Evandro's. Welcome, Evandro. Please start your talk.
Thank you for the introduction, Limichen. Hi, everyone. I'm Evandro. I'm co-founder of QuantumLoop with Claudio Lima. I believe he's the audience. At the end of this presentation, I hope you understand a little bit more about the quantum software programming stack. I will start by first introduction QuantumLoop. We are a quantum computer startup based in Houston and also in Salvador, Brazil, and also have an office in Florianópolis, Brazil. Our mission is to boost the development of quantum solutions. When we say quantum solutions, we mean software accelerated by quantum computers. So for that, today we have three main solutions. We have CAT, that's a Python quantum programming platform that allows you to develop a quantum application. We also have a collection of high-performance quantum computer simulators that use multi-GPUs to accelerate the execution of quantum algorithms. It's very useful for research and education when we can speed up the execution of quantum software. And to execute quantum applications on real hardware, we have QBridge. That's our quantum computer operation system. It's basically providing an abstraction layer for calibration and also for high-level quantum programming. So a little bit more about CAT. CAT basically lets anyone to develop a quantum application using Python. The objective of the platform is to bring all the expressivity from Python to quantum programming. It provides a built-in quantum simulator that uses multi-thread execution that allow you to execute a quantum application directly on your own computer. It also provides a backend, a quantum compiler written in Rust that's very performing classically and also produce code that is very performing quantally. CAT is available right now in quantumcat.org with a open source license. So to execute CAT programs on a quantum computer, one solution is QBridge. QBridge is our solution for quantum computing operational system. It basically provides a hardware abstraction layer that allows you to implement calibration routines that calibrate the physical quantum computer and also automatically manage these calibration routines. So you can take the best of your quantum hardware and reduce the need for human resource to maintain this quantum hardware. And also just providing a high-level interface for quantum programming platforms as CAT and in the future for Qiskit and other programming platforms. This is a hardware agnostic solution, so we can work with different quantum chip implementation and also different quantum interfaces. For example, from Qiskit to quantum machines and others. And also QuantumLoop, we begin in 2021 with a partnership with Senai Smatec. Senai Smatec is the larger computer center here in Brazil, for Center for Research in High-Performance Computing. Use the supercomputers from Senai Cimatec, and also we collaborate with Senai Cimatec to create the quantum innovation, quantum industrial innovation. That is a center of competency for developing quantum solutions for the industry. We are also member of the NVIDIA Inception program. We have software available that is our quantum simulation solutions available on the AWS Marketplace and also on the Microsoft Azure Marketplace. So for the presentation, the message at the end of this presentation, I'm convinced you that the quantum software is as important as quantum hardware. We needed to develop quantum hardware, but alongside quantum hardware, you also need to develop software, quantum software. Imagine having all the computational power we have today with all the GPUs, TPU, but still programming using Fortran, for example. Imagine how this would impact innovation. So, as quantum hardware improves, we also need to improve our quantum software solutions to take the most of this hardware. So in this talk, my objective is to show how can we translate human readable code, this is high-level quantum programming using Python, into quantum instruction. Those are the low-level instructions that the quantum computer can execute, basically the binary for the quantum computer. So to best situate my talk, I want to introduce the quantum loop ecosystem. So you can really say what is this, where is this translation? So in our ecosystem, we have quantum solutions. We have quantum solutions for finance. We have quantum solutions for chemistry. The input of those solutions, those are softwares with the interfaces that you, for example, a domain specialist, someone that understands chemistry, can use this platform. And this platform, you then make a call to the quantum program platform that's CAT. And CAT, you make the interface to the quantum computer. So basically, we have three kinds of users in our ecosystem. We have the domain specialist that does not need to understand anything about quantum programming, quantum computer, only in their domain. For example, a specialist in finance. We also have a quantum developer. The quantum developer does not need to understand how the quantum computer is implemented. It does not need to understand if it's a trapped ion implementation, it's a superconductor quantum computer. It needs to understand the logic of quantum computing. And also understand a little bit more about the quantum solution. Not how to take the best of the solution, but how to translate from, for example, a finance domain to a quantum domain. And the quantum developer will use CAT for this development. CAT, the code generated by CAT is hardware agnostic. This means that the program does not need to know where this code will be executed when he's programming. And it's the job of CAT to take this high-level instruction and break it down into the steps that, for example, a quantum computer can execute. So, for example, take the quantum program from CAT and run it on the QBridge. And on the QBridge side, we have our quantum engineers that does not need to understand anything about the quantum solutions, not even understand how to implement our quantum algorithm, but it needs to understand how the quantum computer works fundamentally, how it's implemented, how it's physically controlled. So it can implement the calibration routines to take the most of it. So in this talk, we're going to focus on the translation from the quantum programming platform, that's CAT, into the instructions that a quantum computer can execute, that a QBridge can execute, or for example, another quantum can execute, quantum computer can execute. So we're going to break down this talk in two parts. First, we're going to focus on quantum compilation. That's break down high-level instructions into low-level instructions of the quantum computer. But we're also going to talk about quantum measurement. Sometimes the challenge is not on how to implement this circuit, but how can we measure the circuit to take the quantum information from the quantum world to the classical world. So we're going to see quantum measure at the end. So we start with quantum compilation. More precisely, what I'm talking about. We're going to see how a code, for example, a quantum code written cat we have here, that is hardware agnostic, meaning that it can run on any quantum computer given it has enough qubits. It can run on any quantum computer implementation, for example, trapped ions or other implementations. Also, quantum code can be input size, can work on arbitrary input size. In this implementation, we're only taking the qubits variable here. There is no information on how many qubits there is here. We're just operating on how many qubits the quantum programmer wants. And we're gonna take this quantum code and select a target QPU. For this example, we're gonna take a very small QPU, a 20 qubits QPU, that only implements 3 qubit gates. This is a 2 qubit CZ controlled Z gate. This is just 2 qubits, different from this one, that's arbitrary number of qubits, and 2 rotation gates. And also, the qubits are physically distributed like this graph. And this 2 qubit gate, the CZ gate, can only be operated between neighbor qubits. We cannot make a CZ gate between qubits that are not physically connected. So we're going to take this quantum code on the left, execute this for 10 qubits, 10 qubits out of this 20 qubits, and at the end, we're going to see this final quantum circuit here. So we're going to see how can we take from this Python implementation to this low-level quantum circuit that only uses those 3 qubit gates, sorry, those 3 gates, that 2 qubit gate here, the 1 qubit gate here, the rotation, and how we're going to end up with this circuit. So first step, we need to understand what's going on with this code. Here we have a more explicit version, a standard version of this code, implementing exactly the same thing, but using more lines of code without the things that we have in cat to reduce the number of lines. So in the expanded version, we can see Hadamard gates being called, X gate being called, and I controlled the Z gate. That's a multi-qubit controlled Z gate. And on the right here, we have a high-level quantum circuit. The quantum circuit diagram is very interesting because we can represent the high-level instruction and also low-level instruction using the same language. So here we have a high-level circuit. This high-level circuit is for 10 qubits. Now we need to say how many qubits there is. On the quantum code, we don't need to say how many qubits there is. So we're going to execute this for 10 qubits. We can see the Hadamard gate being applied here, the X gate being applied here, and you can see this multi-controlled Z gate. That's a qubit gate that operates between 10 qubits. There is no quantum computer that can implement this within one execution. We need to break it down. And then we have the X gate and Hadamard gates again. On the concise version, we are only using this concatenation. We are concatenating these 2 gates, the Hadamard and the X. You're going to see here. Then we are calling this CZ gate for all those qubits here. And the with around instruction allow the compiler to say that you're going to take this gate and inverse this at the end of this call. So we automatically are calling those 2 gates at the end here. With this, we can reduce the number of lines code, but we can also implement some optimization that's not in context of this talk. But it's a very interesting quantum instruction. So now we have a high-level quantum circuit. We need to compile this quantum circuit. We have 3 main steps. First, we need to decompose this multi-qubit gate in the middle here into a sequence of 1 and 2 qubit gates. More precisely, those 2 qubit gates need to be that CZ gate. Then we need to take this decomposed circuit and map those logical qubits that we have here into physical qubits. That are the qubits on the QPU. And we need to make a mapping adapting the security that we have to the connectivity constraint of the QPU, making sure that the two qubits that are not neighbors, we don't have a CZ gate between them. And lastly, we need to translate single qubit gates into the native gate set of the QPU. So first step, breaking down the multi-qubit gate. Break down the multi-qubit gate. Here we're gonna we see that we're gonna take these 10 qubit gates here, and then we're gonna break it down on using only 10 qubits. This is the best we can do when we don't have any information about the target QPU. But you see that this circuit here is way longer than this one that I showed you before. What's going on here? When we don't know the target QPU and we want to make the decomposition, for example, before the quantum compilation, we cannot take the advantage of qubits that are not being used on this QPU. To be more precise, imagine that we have this 10 qubit QPU, and we know that out of these 10 qubits, we are using, out of the 20 qubits QPU, we are using only 10. This means that we have more 10 qubits that are not being used. And the compiler can use those 10 qubits more to reduce both the classical execution time needed to decompose this gate and also the number of gates needed to represent this on the final circuit. So it's an optimization of the compiler. The compiler knows how many qubits are being used right now and how many qubits there are available, so we can make the best choice of the decomposition algorithm. This is something that the programmer cannot know, because the programmer does not know exactly in where this code will be executed. It may know today, but tomorrow a new computer can arrive with more qubits, and the compiler will make a better job decide on the decomposition algorithm. So once we make this decomposition, we need to take this quantum circuit and map it into the connectivity constraint of the QPU. So for example, our 20 qubits are placed like this graph here, and only the neighbor qubits are allowed to have a CZ gate. What's the CZ gate? Is that this line here. I believe this line is small, but at the end of each line, it represents where these qubits are connected. And once you make the circuit mapping, there will be only CZ gate between qubits that are physically connected. How we can do this? We need to take those logical qubits that we have here and map these into physical qubits. And we need to, once we map, we need to move those logical qubits in our physical QPU. How can we move those logical qubits? Applying a swap gate. As we don't have a swap gate natively on this quantum computer, this example quantum computer, we can, for example, make a swap using 3 CZ gates. So this is the end of the compilation on the classical computer. So we're gonna implement our application on the classical computer. We're gonna press start, press run on the classical computer. It will compile this application locally, and they will send this quantum circuit to the quantum computer. However, this is not the end of the compilation process. At the quantum level circuit, and replace each quantum gate with a pulse sequence. This pulse sequence is what controls the physical qubit. So this is not the last step of the compilation. However, last step, that is taking the pulse sequence, we need information about the qubit calibration. So we cannot make this last step on our computer locally offline. We need to have information about the last calibration. And calibration can occur every hour, every minute if you, minute is not so, but every hour if you choose so. And also, to generate this pulse sequence, the quantum computer have specialized hardware that can make it more efficient, and it can generate gigabytes of information that we don't need to pass to the internet. So best leave to the quantum computer to do this last step. So going forward, let's talk about quantum measurement. My objective here is to show a simple code and show how different ways to measure the qubits can lead to better results. For that, I'm using the Falcon algorithm. It's the feedback quantum optimization algorithm, feedback-based quantum optimization algorithm. This is a versional algorithm that's for optimization problems. And it's very interesting because it does not need to have a classical optimizer. We can execute layers of this code here. We have here an implementation for the problem max cut. And at each layer, we can measure a parameter beta. How we measure this parameter modify a little about the algorithm. But we need to define two Hamiltonians. We have a problem Hamiltonian, a driver Hamiltonian. This is for the max cut implementation. This is the mathematical definition that people from physics like to use. This is the implementation use and cat. It's basically a one-to-one mapping between the mathematical representation and using the functions in Python. But we do not measure directly these Hamiltonians. We have two ways to measure those Hamiltonians. We have, for example, a first-order derivation that will measure the commutator of the driver and the problem Hamiltonian. And we have a second-order measurement that we measure a more complex Hamiltonian, defined like this. We will not go into details what's going on here. But for a very specific example here, a graph with 4 edges, we executed this algorithm with just 5 layers. And at the end of these 5 layers, we're gonna measure the number 5 and 10. It's just an example. So at the end of these 5 layers, using this first order derivation, we have 60% of chance to measure the correct state. However, if we change how we measure this parameter better, at the end, we will have 96% chance of measuring the correct state. It's a huge difference here. But what's the catch? For this Hamiltonian, we need to execute. We have each observable. What is observable? An observable, it basically is a formation, is a circuit that we need to measure. So basically, we need to have 80 jobs, send it to the quantum computer, and execute it short times to take this result. So one beta measurement is 8 execution. On the second order derivation, one beta measurement is 28 executions. So the quantum circuit is exactly the same. The Hamiltonians is exactly the same. It's just how we implemented this beta parameter. And this is for just 4 edges. As we grow the number of edges on our graph, the second order derivation measurement of beta will increase greatly. And this is a problem that is not very hard on the number of observables. For example, quantum chemistry is way more demanding on the number of observables. So we need to have better strategies to measure those, for example, beta parameters. We cannot use a naive measurement that for each observable, we just make one one job. So in the quantum programming stack, we also need to have something like a expansion value engine. This expansion value engine, you have implementation implementing quantum measurement optimizations. Those are optimizations to reduce basically the number of executions we need to do. So with, for example, 28 observable, we don't need to have 28 executions. We can have less. There's not one size fits all. There's three main optimizations today: classical shadow, qubit-wise commutativity that explore the commutativity of qubits, full commutativity. And as there's no one size fits all, the quantum compiler needs to implement not all, but most of these measurement optimizations. So the programmer does not need to worry about how many times you will execute the measurements. The programmer only need to worry about implementing these Hamiltonians and the quantum circuit, and the optimization is left to the compiler. Alongside with quantum measurement optimization, we also need to have a gradient calculation. For example, a variational quantum eigensolver that's used for chemistry can be executed in less steps if you have gradient calculation. In the quantum computer, we cannot do backpropagation to get the gradient, so we can have, for example, parameter shift rules for the gradient calculation. But again, the program does not need to understand how this is implemented, or maybe just the performance associated with it. And it's part of the quantum compiler to implement all those strategies. So at the maximum, the programmer will choose one of them. So to conclude, I expect that this presentation show you how a quantum programming platform like CAT or any other is necessary to take the most of a quantum computer. With CAT, we can take a very simple code and execute this in the quantum computer. However, we cannot execute this directly. We see that how the complexity of this code increases as the compilation steps go further. So at the end, we have this circuit. We cannot implement this with a graphical interface with drag and drop gates. And this is just a 20 qubits CPU. With 100 qubits, imagine it's not feasible to use those kind of by hand placement of gates. So we need to have a quantum programming platform to make a quantum computer useful. It's not an option. But also, high-level quantum programming has several benefits. For example, it can enable deeper optimizations that the programmer does not need to know about this optimization. The compiler will explore this optimization for the programmer. Also, it's provided portability across quantum hardware, not only between quantum hardware that we have today, but portability across future quantum computers. And also, a quantum programming written using high-level quantum programming language today, in the future, can execute way faster as new compilation techniques are developed. And these new compilation techniques can optimize this circuit. So we can have a quantum program written today that executes in a quantum computer of the future with more performance than we have available today, because the compiler have updated, and now we can explore more optimization, and your code is faster with zero work. So I believe my time is very, very short. If you have questions, you can contact me at evandro@quantumloop.com. I don't know if you have any time for Q&A. But if not, you can contact me at evando@quantloop.com. And thank you very much for your attention.
Thank you, Evandro. I don't think we have time for the questions. We received 3 questions. Please contact Evandro directly for those questions. Thank you for the presentation.
Thank you, Lenin. Thank you, everyone, for the attention.